Traditionally, there's another way to test for the significance of the regression. That is to say, to test for the null hypothesis that the slope is equal to 0 against the alternative that the slope is not equal to 0. You can use an analysis of variance, ANOVA. The analysis of variance information is given in the following table. You're going to have 3 rows worth of information. These rows refer to the source of variation in your data. Roughly speaking, you can explain a fair amount of the variation due to the regression. You can explain how y changes in terms of the value of x based on the regression, and you can also explain the rest based on the error, which is basically everything which is not explained by the regression. There might be another predictor that you didn't have access to. Or it could be that the linear fit wasn't that great of a fit, and there's going to be a fair amount of error. Combined, you explain the total variation. For each of these sources of variation, you have a corresponding sum of squares. SSR, SSE, SST. So this is the sum of squares for the regression, sum of squares for the error, and the total sum of squares. Each of these sums of squares has an associated number of degrees of freedom. The source of squares for the regression has the sum of squares for the regression is 1 degree of freedom. The sum of squares for the error has n-2. We've already seen this. And if you add up these degrees of freedom, you get n-1 for the total sum of squares. Associated with the regression source of variation and the error source of variation, you have a mean squared sum of square. You have a mean square quantity. MSR for the regression, MSE for the error. Mean square regression, mean square error. And these are obtained, we'll see later, by dividing the sum of square to which they correspond by their associated degrees of freedom. So MSR would be SSR divided by 1, MSE would be SSE divided by n-2. We've mentioned briefly that the mean squared error follows a chi-squared distribution with n-2 degrees of freedom, while the mean square regression component follows a chi-squared distribution with 1 degree of freedom. We can compute the ratio of MSR to MSE. It's the ratio of chi-squared distributions, and we've talked about ratios of chi-squared distributions a number of videos ago. This actually gives us an F distribution. So the ratio we get here, that's a computed quantity. MSR is specific to the sample that you have to run your regression. Same with MSE. When you compute the ratio, you get a specific value. It's an F statistic. And you can compute a corresponding p-value, the probability that you would expect the ratio, MSR to MSE, to be greater than this F statistic if things were happening completely by chance under the null hypothesis that beta 1 is equal to 0. Let me show you what some of these quantities are really going to look like. The F statistic follows an F distribution with 1 degree of freedom, which corresponds to the regression source of variation, n-2 degrees of freedom, which corresponds to the error source of variation. So the F distribution has 2 parameters, n1 and 2. In the case of the ANOVA table, n1 is 1, n2 is n-2. And the sum of squares for the errors would be the square of the differences between the actual observations and the predicted ones, so the residuals. The sum of squares for the regression is the sum of the squares of the difference between the predicted value, so the regression values of yi, and the average value of the observations y. And the total sum of squares then would be the sum of the squares of the difference between the observations and the average value of the observations y. One of the things we do get is that the sum of squares of errors plus the sum of squares of regression is actually equal to the sum of squares total. The mean square for the regression, it's the sum of squares for the regression divided by 1. The mean square Error is the sum of squares, error divided by the degrees of freedom, n-2, and the F statistic is the ratio between MSR and MSE, the same thing as SSR divided by 1, divided by SSE divided by n-2. And this SSR divided by 1 under the null hypothesis follows a chi-squared distribution with 1 degree freedom, and the MSE follows a chi-squared distribution with n-2 degrees of freedom, which is why this quantity here actually should follow an F distribution with 1 degree freedom and n-2 degrees of freedom. So how do we use this table to answer our original question, to test for the null hypothesis of lack of significance against the alternative hypothesis of significance? We still have the same rejection region, like nothing has changed here, it's the same data. We can still test for the null hypothesis that beta 1 is 0 by determining if the standardized quantity here, point estimate for the slope minus the candidate 0 divided by the square root of the MSE divided by SXX, if that's greater than the critical value of the student t distribution with n-2 degrees of freedom at a confidence level of alpha divided by 2, but you can also write it as this expression here. Is the F statistic greater than the critical value at confidence level alpha of the F distribution with 1 and n-2 degrees of freedom? And this is a value you obtain from your tables. These two things are equivalent. For the fuels data set, you can go through the process, build a table. I'll show you how to do that in the video using R, and then you'll get a F statistic of 128.9. That's actually pretty high. That's actually a pretty large value. But we need to compare it to, at the 5% confidence level, the critical value of the F distribution with 1 and 18 degrees of freedom, which you can either obtain from the tables or by computing the critical value in R. Right? Critical value of the F distribution, this is the F part. Q here represents a quantile. You want 95% quantile, and you have 1 degrees and 18 degrees of freedom for the F distribution. And you'll get that this value is about 4.41. Because the F statistic is in the rejection region, the critical region, we reject the null hypothesis in favor of the alternative hypothesis that the regression is actually significant when we work at the 5% confidence level. But you could decrease the value of alpha here quite a lot and still reject the null hypothesis. The data that we have so clearly supports the significance of the linear